So here we are using the standard basis of a polynomial p sub 3. So we have our basis b is defined as 1t squared t cubed, and we want to use the coordinate vectors to test the linear independence of the following set of polynomials. So what we want to do here is, again, take each one of these polynomials and think about their coefficients to rewrite them as a vector. So we want to rewrite the given polynomials So I have, the first polynomial is 1 plus 3t squared minus t cubed. And so we can say that this first polynomial, p sub 1, is defined by the column vector 1, 0, 3, negative 1. We have the second polynomial in the set is t plus 3t cubed. So p sub 2 is the column vector defined as 0, 1, 0, 3. And then last but not least, we have our third polynomial here, 1 plus t plus 3t squared. And so here our polynomial p sub 3 is defined as 1, 1, 3, 0. And so we want to determine if these three vectors are linearly independent. So let's recall the definition of linear independence here. We want to recall that a set of vectors, say p sub 1, p sub 2, p sub 3, are linearly independent when the vector equation c sub 1 times vector p sub 1 plus c sub 2 times vector p sub 2 plus c sub 3 times vector p sub 3 are equal to the 0 vector. So when this homogeneous equation has only the trivial solution. So what we can do here to test this is convert this vector equation to an augmented matrix to make sure that we end up with the 0 vector. So let's row reduce the augmented matrix p sub 1, p sub 2, p sub 3 with our 0 vector to row reduced echelon 4 to test if this is linearly independent or not. And so let's give ourselves plenty of room. So we want to put those three column vectors into our matrix. So we have p sub 1 was 1, 0, 3, negative 1. P sub 2 was 0, 1, 0, 3. And p sub 3 was 1, 1, 3, 0. And we're augmenting this with our 0 vector. So we're ready to row reduce. So I take my first pivot and I want to use it to eliminate the entries below it. So we'll need to do minus 3 times the first row plus the third row to attain that new third row. And then we can simply add the first row to the fourth row to attain the new fourth row. So this will give us the equivalent matrix 1, 0, 1, 0, 1, 1. Then we have minus 3 plus 3 is 0, 0. And then we have negative 3 plus 3 is 0. And then we'll have 1 minus 1 is 0, 0 plus 3 is 3, and then 1 plus 0 is 1. So we should immediately bring this third row here down. So we'll interchange the third row with the fourth row. To attain the equivalent matrix, we have 1, 0, 1, 0, 1, 1, and 0, 3, 1. And then our row of zeros is in that fourth row. And let's move this one over. All right, so our first column is all set. So we now want to go ahead and take that second pivot and use it to eliminate the entry below it. So we'll do minus 3 times the second row plus the third row to attain the new third row. And so this gives us the equivalent matrix, the row equivalent matrix, 1, 0, 1, 0, 1, 1, 0. So we have negative 3 plus 3 is 0. Negative 3 plus 1 is minus 2, 0, 0, 0. And so we're excited here. We can see that we have attained echelon form. And we can make our final conclusions. And we can say that since the matrix has 3 pivots, since the matrix has n equals 3 pivots, right, a pivot position in each column, then the columns of the matrix, which are defined as the set of vectors p sub 1, p sub 2, p sub 3, are in fact linearly independent, which further allows us to conclude that therefore the polynomials are also linearly independent. And this is our beautiful final answer.